Yeah, welcome to our subsurface scattering session, the second session on the MAM workshop. We will have two talks in this session, and we will start with the first talk on by Murat Kurt from Ege University in Turkey, and he will tell us about a genetic algorithm based on heterogeneous subsurface scattering representation. Murat, we are looking forward to your presentation.
In this paper, we present a novel heterogeneous subsurface scattering representation, which is based on a combination of singular value decomposition and genetic optimization techniques. In the field of computer graphics, photorealistic representation of optical thick translucent materials requires modeling of the BSSRDF, which is a generalization of the BRDF, introduced by Nicodemus et al. The diffusion equation is a well-known approximation technique that is used to represent homogeneous translucent materials. The most of the homogeneous subsurface scattering models used in computer graphics community are derived based on this approximation. As the optical properties of heterogeneous translucent materials exhibit spatially varying distributions, measuring the optical properties of heterogeneous translucent materials results in the large data size. Therefore, a number of data-driven subsurface scattering representations have been proposed to represent measured heterogeneous subsurface scattering data compactly and accurately. But it is still an investigation issue to represent measured heterogeneous subsurface scattering data compactly and physically accurately. Therefore, we focus in this work on the compact and accurate representation of this special component of heterogeneous subsurface scattering. We will use a combination of genetic algorithm and singular value decomposition techniques for this. In order to create a good representation, we need to study the structure of the heterogeneous subsurface scattering. Optical thick translucent materials can be decomposed into two classes, namely homogeneous and heterogeneous. While optical properties of homogeneous translucent materials are constant, heterogeneous translucent materials exhibit spatially varying optical behaviors. Therefore, measuring and modeling of heterogeneous translucent materials are much more complicated than homogeneous translucent materials and requires much better understanding of light and material interactions beneath the surface. In this work, we use Pierce et al.'s and Song et al.'s heterogeneous subsurface scattering measurements, which include multiple measurements in a single image. Therefore, we need to preprocess these raw measurements. Preprocessing includes two steps, namely extracting kernels and linearization. After these operations, we get two-dimensional subsurface scattering matrix, and this matrix can be used in the rendering algorithms. To show how we prepare our subsurface scattering matrix, let's consider the following one-dimensional illustrative example. A planar sample consisting of a single material exhibiting homogeneous and subsurface scattering. This sample contains a single heterogeneity, a light-blocking vein, that blocks a light going from the left side of the sample to the right side and vice versa. We are now going to construct the subsurface scattering matrix RD, which is parameterized over incident illumination surface points xi and exited point xo. For simplicity, we assume that xi and xo are parameterized identically over the sample surface and that both have the same resolution. Each row in this matrix is the observed response of the material of illuminating a single incident point. In our case, a projector was used to illuminate surface points, and the observed camera images is copied into the corresponding row of RD. We can repeat this for every incident position and row. Note that when a point close to the light-blocking vein is illuminated, that a part of the homogeneous response is cut off. Scanning all points yields a matrix that looks something like this. A few important observations can be made regarding the structure of this matrix. First of all, it's a band diagonal matrix. Diagonal band is the result of the homogeneous subsurface scattering. This band is interrupted by horizontal and vertical discontinuities. These discontinuities in the matrix RD are caused by the heterogeneity. Now, this all well for this scientific example, but how well does this observed structure correspond to a real subsurface scattering material? For this purpose, we consider this slab of marble. On this slab of marble, we are going to illuminate each point on this line, and we are going to observe the responses also on this line. I don't know if you can see it, but the discontinuities are in the left top. The reason why these discontinuities are not as underlined as in the synthetic case is because the veins in the marble do not block the light transport completely. In order to better bring out these discontinuities, we are going to reparameterize the matrix RD by sharing it, resulting in a matrix RD prime. As you can see now, discontinuities are much better visible. Another thing to notice is that horizontal and vertical discontinuities have now become horizontal and skew diagonal discontinuities. This is also clearly visible in the reparameterized matrix RD prime of the marble sample. This example empirically validates our conclusions regarding the structure in the subsurface scattering matrix. Note that the width of this part in the matrix is dependent on the amount of light blocked by heterogeneity. Thus, in the case the veins would block all light, then we get a similar situation as in the synthetic example, and this region will be very thin. Indeed, the most compact form of the measured subsurface scattering matrix is the RD prime. RD prime can be represented instead of RD. To find the best transformation for measured subsurface scattering data, we try various transformations using our GA to measure dataset from Pedersen et al. And Song et al. GA is a machine learning technique for solving both constraint and unconstrained optimization problem by imitating the biological evaluation process, including the natural selection. We apply GA to find new transformations for real-world subsurface scattering. The key idea behind GA is that it repeatedly updates the population of individual solutions, culling undesirable ones and allowing the fittest ones to survive. A single such individual solution is referred to as a chromosome, and each element of the chromosome is referred to as a gene. At each step, the algorithm selects solutions at random from the current population. These are treated as parents, and the algorithm uses these to produce children for the next generation. Over successive generations, the population evolves toward an optimal solution based on a fitness function. We also applied both GA and FPINCON optimization techniques to find the fittest transformation. These optimization techniques are readily available in MATLAB library. On average, transformation ID tree with GA decreases the root mean square error much more than the transformation ID tree with FPINCON technique. Therefore, we select and use transformation ID tree with our GA framework. In this figure, you can see our genetic optimization framework. We investigate various transformation and chromosome combinations through our genetic optimization framework. Our final subsurface scattering model will be the sum of the estimation of model errors and the first factorization of RD prime prime. To visualize our results, we implemented a rendering scheme similar to Pedersen et al. In the Mitsuba rendering system. Furthermore, we used a standard texture mapping to apply a material model to a mesh. We validate our model on 8 different real-world translucent materials. This table gives an overview of the modeled heterogeneous translucent materials and a list a number of statistics for our model based on a typical value for K. We compare measured and modeled subsurface responses of selected surface points. The sub-edit representation may show radial symmetric behavior as some materials due to the parameterization used, which may be insufficient for representing heterogeneous materials accurately. We also compare measured and modeled subsurface models. The comparison outlines show that our model represents heterogeneous translucent materials more accurately for comparable data storage requirements. In this work, we present a GA-based heterogeneous subsurface scattering model. In the future, we plan to investigate real-time rendering algorithms to implement our representation in screen space. I hope you enjoyed this presentation, and I thank you for your attention.
Yeah, thank you for this very nice and inspiring talk. And so far, I do not see questions. But let me start. Please, I encourage you to ask questions. If you have questions to Murat, let me start with one. And I would really be interested in how fast the algorithm is. Can you tell us a little bit about the timings? And can you tell us about how the timings are influenced by the use of different layers?
Actually, the timings of the algorithms can be considered as two aspects. For the fitting times, genetic algorithm is a little bit slow than other optimization techniques because it handles various solutions which can be considered as a chromosome. So it handles a population. So fitting times is a little slower than other optimization techniques. But we find that our genetic algorithms finds the transformation ID tree as a solution. Our computation times, because of the transformation ID tree, is a little faster than other modeling techniques. And this shows us that our subsurface scattering representation can be implemented in real-time rendering algorithms. So it is our future work to implement our subsurface scattering representation as a real-time platform. So maybe it is in a mobile platforms or other real-time platforms.
Yeah, and can you tell us something concerning the layers, how they influence the overall computation time?
Layers is really effective on the computation time of our algorithms. If you want to do a real-time rendering, if you want to use our subsurface scattering representation in real-time rendering algorithms, we must choose our number of layers as small as possible. In our preliminary results, our algorithm, our representations gives acceptable results. It's a fair number of layers. But if you want to use our subsurface scattering representations in offline renderers, we can choose our number of layers as high as possible, such as 10 or maybe 25. And then we get very accurate results. But our model will not be very compact, and computation time of our algorithm will be a little higher.
Okay. Maybe I can encourage the others to ask more questions. I currently take the questions only from Rocket. Maybe you can formulate your questions in Rocket, because I think we still have some time for one or two more questions. No, otherwise, I think if there are no more questions on this paper, we thank Mort again. Thank you very much for the nice and very good presentation. And then we will continue to the second talk, which is about on the nature of perceptual translucency, a perceptual talk, and the talk will be presented, or the work will be presented by David Gigilashvili from the Norwegian University of Science and Technology in Gjøvik in Norway. Please.
Hello, my name is David Gigilashvili, and I'm going to present my position paper about translucency perception. So it's called On the Nature of Perceptual Translucency, and I have co-authored this paper together with Jean-Baptiste Thomas, Yngve Hardeberg, and Marius Pedersen. Let's start with the content. So today I'm going to describe the motivation of this work, and then I will present the open questions that exist in studies of perceptual translucency, namely definition and conceptual understanding, perceptual dimensions of translucency, relation with transparency and opacity, how to quantify perceptual translucency, and the translucency constancy of objects and materials. And finally, I will conclude with some final remarks. Let's start with the motivation. So translucency is an ambiguous term. So if you ask a random person what translucency means, you might get an odd look. And even among the experts of the field, there is no single agreed definition of translucency. These uncertainties make the perception research difficult. It is difficult to design the experiments because if we do not know what translucency exactly is and how our subjects would interpret that, then how should we ask the question? How should we select the question? Then it's difficult to interpret the results because we don't know exactly how the task was interpreted and performed by the subjects. It's difficult to communicate with the scientific community because this potential misunderstanding and disagreement on the concepts, and if we do not have agreement on these points, also reproducibility of the research might be compromised. Definition and conceptual understanding of translucency is a big topic. So here I brought several examples how translucency is defined in the literature, like property of a specimen by which it transmits light diffusely without permitting a clear view of objects beyond the specimen and not in contact with it, and two subsequent definitions also mean some kind of light diffusion or scattering inside the volume and blurred image, while the dictionary definition, so non-academic ordinary dictionary definition, is has both aspects. It can be either transmitting and diffusing light, so making it blurred and not clear, or it can be clear, transparent, synonymous with transparent, and furthermore, even the second meaning that is more indirect meaning, we see that translucent might mean free from disguise and falseness, so it might be related with something clear. So this disagreement exists because the definition does not say what is the relation with the physical properties or perceptual properties. So when we define the translucency and talk about that, what do we mean? Do we mean translucency as a physical material property, so the description of the subsurface light transform, how the light is absorbed, scattered inside the volume, what is a phase function? Do we talk about this, or do we talk about perceptual translucency, people perceiving material to be translucent, perceiving it to possess some translucency. And even like if we highlight that translucency is scattering of the light, what kind of scattering do we mean? Is it volume scattering or it's surface scattering? So if the volume is transmissive, but surface roughness makes material impossible to see through, is it translucent? Or how much scattering do we need to consider material translucent? Is it like too much, or even a slight blur is enough? These are the questions that we do not have answers on. And what if a subject is confused in the experiments? Usually subjects are provided with clear definitions they have to stick to, but how should we define it if there is no definition for them? How should they interpret the task? Perceptual dimensions of translucency is another interesting topic. For color and gloss, we have seen some dimensions. For example, color can be characterized by its like hue, chromaticity, lightness, and even for gloss, there have been several dimensions proposed. It can be specular gloss that is quantified, it's contrast gloss, or distinctness of reflected image, or absence of bloom, and so on. But what about translucency? Does it have separate perceptual dimensions? How would we quantify these dimensions? Or is it like clarity and haze that is usually used in like metrology that can be correlated with perceptual dimensions? Can we quantify how clear the image is with translucency? That's also an open topic. And furthermore, what complicates the problem is its unidentified relation with transparency and opacity. We know that transparency, opacity, and translucency, all three relate to some kind of property about transmitting or blocking the light. But how do they exactly relate with one another? Are they mutually exclusive, or is it more like fuzzy boundaries among those? For example, if we refer to the image on the left, the object E, we can see this is from this image is from our paper about the research how caustics, presence of caustics impact perception of translucency. And for object E, the caustics are the only cue that tell us that this object is translucent. Otherwise, if we have a look at the object, there are no cues. It looks fully opaque. There are no cues we could tell that it is translucent. And also like object D, caustics show how the light is transmitted through the object, and object F is also very informative in that sense. So then the question is, can a material possess some degree of transparency and translucency at the same time? Can it be transparent and translucent, or can it be translucent and opaque at some extent, or are those concepts mutually exclusive? And in any case, when do transparent materials start to be considered translucent? So when we tune the material properties, when they become considered translucent, and when do translucent objects become opaque? So is there any clear threshold? We think that there is no single threshold, and opacity and transparency are not the discrete points of the discrete extreme points, but they are rather sections across the spectrum. And we believe that this kind of bell-shaped curve describes translucency as a phenomena. It can be even even the probability of considering a material translucent. So we start with transparency, and gradually comes the concept of translucency in that play, and then somewhere there is a theoretical extreme where material is very translucent, and then when we increase scattering or other property unknown to us right now, we gradually move towards more opacity decreasing translucency. And how this relates with the problems in perceptual research. So these are the screenshots from our psychophysical experiments. We were studying how object shape impacts perception of translucency differences, and we asked the people the question to so there are like the left image is one trial and the right image is the right pair is the second trial. So two Buddhas and spheres are separate trials, and we asked people a question. So which pair has larger translucency difference? Select the pair with larger translucency difference, and we got confusion, clear confusion from the observers, because for example on the left case they see that there is something that really different about two Buddhas in the top row, but they don't know, is it translucency, is it something else? They see that the bottom pair has some difference in scattering, but they don't know whether the same is happening, so whether the scattering is what differs, what the two Buddhas on the top differ in. And we got responses from many observers that okay, transparent ones, we clearly see there is difference. We don't know what's happening. It may be just lightness difference in the top. So, and they got confused. On the right, the same is happening. We got responses that two spheres are not translucent at all, and they are opaque, so there is no translucency difference. So people do not know how to compare translucency differences. In many papers regarding translucency perception, they conduct experiment asking people to identify, for example, two alternative force choice, to identify similar stimuli by translucency. And then the question is, how do people know what translucency similarity is? Can they really isolate objects by translucency, or they are tempted to decide by other cues like lightness? For example, many observers of us have admitted that they decided by lightness. So even if they provide an answer, we don't know whether that really corresponds to what they perceive. They decide by lightness, darker object, lighter object, because they could not isolate translucency. And on the right-hand side is the result from our experiment, where we asked people to rank objects by translucency. But can you guess which side is considered more translucent? Is it the leftmost one most translucent, or the rightmost one most translucent? I don't remember either, because people have given mutually exclusive answers. It can be like more transparent considered more translucent, or it can be closer to opacity with more absorption, more scattering may be considered more translucent. So ranking task was very ambiguous. How do people rank them by translucency? And then final question, translucency constancy. So similar to color constancy, translucency also might be constant at some extent, but it also fails very fast. For example, on the left-hand side, you see that presence of backlight changes objects, the textile samples from opaque looking to more translucent looking. And there have been works in the state of the art that demonstrate that the backlight makes object look more translucent. And then on the right-hand side, we see that there are two objects, a sphere that has less density of the colorants, and the female bust that should be theoretically more opaque, but because of thin parts, people considered it more translucent, because thin parts transmit light more easily. And so when we talk about translucency, is it material translucency as an absolute property? Is it a physical property, how light travels through the material? or its object translucency, the cues, image cues preserved on this particular object. We don't know this. If we compare this with color, it will be like color that is perceptual, and object translucency is perceptual, and spectral reflectance and material translucency that are more more objective. And we have physiological understanding of color perception. It's like color matching functions, but we don't have translucency matching functions. Do they exist? And here is the example of the image. It's the same material, but the object shape makes one look translucent and the other one look transparent. So to summarize, it's a fuzzy concept, and we question whether standardization is possible. Is it possible to standardize, or it's context specific? And we propose the following update in the definition that should reflect its condition dependence. Thank you very much.
Yeah, thank you, David, for this nice presentation. And I suppose that there are some questions, at least, because I see that people are typing questions. But let me start with the first one. What kind of applications do you have in mind when you're doing this kind of research? Because it's a very basic research, of course, but there are also applications. Where do you see the applications of your research?
Yeah, first of all, thank you very much for your interest and watching my presentation. Yeah, the applications can be diverse. It can be like from pure computer graphics perspective. So when we are modeling material and we want to predict how it will look, but it can be like manufacturing of actual physical objects. So any industry where we need to predict the appearance of a material. So we need to consider how different physical properties will affect the final look. And then when we're on the other way around, when we're measuring it, so we want to have, we need to quantify this to replicate the same look in the future. So it's, for example, if you're producing just like whatever comes to my mind right now, a pen, and you want to have a particular look for this pen, you need to predict the appearance. Then you need to link between physical properties and how the people, the consumers, people who buy your product will perceive its look. But like, again, like this modeling right now is done in computer graphics. I look right now at this from the computer graphics perspective. So when we're generating the stimulus, so how it will look into the viewers, like for example in animations. But okay, the eventual application, I believe, can be moved to manufacturing of the physical products.
Okay, thank you very much. And there is a question by Ilyan Georgiev. Physical size also impacts the subjective translucency of an object. Does this matter for what you are trying to achieve?
Yes, actually, yeah, that's two different things. Like one thing is like geometrical shape. So how many, for example, the histogram of surface to medial axis distances, this kind of shape, how many thin parts do we have, how compact parts do we have? This is one, like a 3D shape itself. And the second point that matters, of course, is physical size, definitely. So we need to consider both. Like with one 3D shape, if it's enormous in size, it might be different, and even if it's very compact and its scale is small, it can be like also affected by that. So yeah, I think we need to consider both when we're talking about shape and geometry in general. It's a scale and it's a shape as well.
Okay. Okay, and then there's a further question by Murat. In which scenes do we better understand translucency? Caustic, spectral rendered scenes, or what kind of scenes do we need to understand translucency?
Yeah, from my experience and experiments I have conducted, translucency is best understood in dynamic scenes. So when the scene is static, when we just show the still photograph, it's difficult to understand. But like I have observed how people solve tasks about translucency, and they the first thing they do is that they move the object, they look for the light source, and they look how the background changes through the object and how moving the objects in different illumination geometries impacts the look of the object. So the dynamics of the scene is one thing that certainly impacts perception of translucency, and caustics can be a very specific case because there might be the scenes. I had one figure in the presentation where there is very little cues about translucency. The object itself might look very opaque, and it's like luminous gradient might also look like similar to the opaque ones, and we can't see through the object. But the caustics might be additional cue saying that okay, there is some transmission happening. So it depends on the scene, and spectral rendered scenes, I think, will bring this like closer to reality, and I think the cues will be more closer to what we actually use in real life, if that was a question.
Okay, I think we are already running a little bit out of time, but there are more really interesting questions, and Gurpreet Singh is asking, to follow up with my previous question, how does opacity differ with respect to translucency?
Yeah, from the results I presented in this presentation, we found that opacity is not a discrete point in the perceptual dimension, and does not necessarily imply complete absence of transmission. So it's more like a part of this spectrum. And my reasoning here was that the boundary between opacity and translucency is fuzzy. So we don't have a clear threshold where we say that, okay, this is translucent, and then from here on it's opaque. So, and the even interpretation of the object is very subjective. It depends on the conditions. For example, when we have backlight, previously opaque materials might start looking translucent, and when we remove the backlight, the other way around. And it also might depend on the application and preferences of the subjects. For example, in terms of applications, transmission of a pen might be neglected, but when we talk about, for example, curtains that we want to block the light entering our room, that's another question. So my opinion on this is that there is no single threshold where we say that, okay, here is translucency, here is opacity. It's very fuzzy, and the boundary is very blurry, and it depends on the application, and like it's specific to particular circumstances.
Okay, thank you for these answers, and also the people who ask you, thank you for the answers. One last question, which I'm really curious about is, did you collaborate with people from 3D printing who are interested in really printing translucent materials, or is this too far from what you are doing?
Yes, actually, also in the presentation, there was one result from one of my papers where I collaborated with Philip Urban from Foundry. Yeah. We have not, we used computer graphics like as a stimuli for the experiment, but the eventual application can be 3D printing. Definitely, yes, that's one of the aims and goal objectives of my research.
Okay, then thank you. This brings us to the end of this session already, because the next session is waiting. The next session will be on material appearance modeling community infrastructure, and I all invite you to join the next session. Thank you all our speakers, Murat Kurt and also David Gigilashvili. Thank you.